Hi everybody. You'll recall from last time we were looking at integer powers of complex numbers. So if z was some complex number and we wrote that in exponential form, so re to the I theta, then we saw that by using de Moivre's theorem, that raising the complex number to the power n, all we had to do was raise the modulus to the power n and then multiply the angle by n. So that was the result that we got. So today, instead of raising a complex number to an integer power, we're going to look at nth roots of a complex number. Well, what does that mean? It means that we want to write down, if we've got some complex number w and we take the nth root of w, we want to be able to see what complex number we get. And that's the same as saying that if we raise z to the power n, what's w going to be? So let's let z be some arbitrary complex number. So z is re to the I theta. And w is also an arbitrary complex number. So let's call it se to the I phi. So it's got a different modulus and a different argument. So if we use the arbitrary expression here for an arbitrary complex number, z equals r to the I theta, and we replace it in this expression, then what we get is z, which we're now writing as re to the I theta, raised to the power n equals w, because w was this arbitrary complex number. Using de Moivre's theorem, we expand out the left-hand side of that equation to get re to the I theta all to the power n equals r to the n e to the I n theta. So when we have two complex numbers that are equal, it's true that their moduli must be equal. So r to the n must be equal to s, and their exponential parts must be equal also. So e to the I n theta equals e to the I phi. So now we've got two separate relationships that we can work with. So taking the first one, r to the n equals s, and if we just take, this is just a real number now, don't forget, so I can take the nth roots of both sides. So if I take the nth root of the left-hand side, I just get r, and that's equal to the nth root of the right-hand side. So that's r equals s to the power 1 on n. When we equate the exponential parts of this though, e to the I n theta equals e to the I phi. So what makes these two things equal is when these give us the same cos and sine. Don't forget that e to the I theta equals cos theta plus I sine theta. So this, because this is represented in terms of trigonometric functions, there are going to be lots of thetas that satisfy this equation. And it turns out that what we need is that n theta is equal to phi plus 2k pi, because this is periodic and k can be any element of z. So now if we rearrange this equation, we just see that theta equals 1 on n phi plus 2k pi, where k is an element of z. So that means that for the nth roots of w, where w was se to the I phi, then w to the 1 on n is just equal to s to the 1 on n, e to the I, and there's a bit of a combination of things here in this bracket, e to the I 1 over n times phi plus 2k pi for k equals 0 all the way up to n minus 1. Now you'll notice that up here I had k was in z, and now I've just got k goes up to n minus 1. Why have I done that? Well, it turns out that once I get past this point, so the nth term in this series will bring me back to the same term that I had when k was equal to 0. If I put n plus 1, that will take me back to when k is 1. N plus 2 will take me back to k plus 2. So I've only got exactly n roots that are going to come out of this, and everything else is just going to then cycle around the roots that I already have. And we'll see how that works when we do an example. So the notes you have on the next page just start off by telling you what I already said. So when we've got k equals 0 to n minus 1, we get n different roots of the complex number w. We stop at n minus 1 because once k is equal to n, we're adding on a whole multiple of 2 pi, so we enter the argument, so we end up getting back to the same complex number as k equals 0, and then we just cycle around through all the roots that we already have. So that's the first thing to notice. The second thing is you don't need to memorise the formula. If you just think of starting always like this with z to the n equals w, and then expressing these things in polar form, polar exponential form, then you can always figure out what the formula should look like. So if you're not good at memorising things, just remember how we derived this on the previous page. So the example asks us to find the cube roots of 8 and then sketch them in the complex plane and express them in Cartesian form. So there's a few things we need to do for this example, but the first thing is we need to find the cube roots of 8. So you'll recall that over the real, so if we're trying to solve that equation over the real numbers, then there's only one cube root of 8. So the only number that has cube equals 8 is 2. Okay, so a cube root of 8 is 2. That's the only real number that has the property that it cubed equals 8, if we're in the reals. But we want to solve this in the complex number system now, so we're going to get something that might be a little bit different. So the equation we're trying to solve is which complex numbers z have the property that if I cube them, then I get the answer 8. So that's what we mean by a cube root of a number. So it's just a number that has the property that if I cube it, I get 8. And the way I'm going to do this is I'm going to write this in complex exponential form. So how do I write 8 as in complex exponential form? Well, if you think about where 8 is in the complex plane, it's just along the x-axis, and its distance from the origin is 8. So this is going to be 8, so that's the modulus of the complex number, e to the I times 0, because the angle that I have to go through is 0 because I'm actually on the x-axis. And that equals 8e to the I 0 plus 2k pi, where k is in z. So this just says that if I take the angle that I've got, which is 0 here, and I add on integer multiples of 2 pi, then I've actually got the same complex number. I go all the way around and I'm in the same place if I add 2 pi. If I add 4 pi, I go around again. If I add 6 pi or subtract 2 pi, I go in a clockwise direction. But 0 plus 2k pi, if that's my angle, it's going to give me exactly the same complex number. So what I'm going to do now is I'm going to think about the cube roots of this complex number. So if I take the cube root of the right hand side, z cubed, then I just get z. And if I take the cube root of the right hand side, it's 8, the cube root of 8, e to the I 1 over 3, 0 plus 2k pi. And you'll see that when we work this out, we have k equals 0, 1 and 2. So we stop when we get to n minus 1. Our n here is 3. Okay, so if we take the cube root of 8, we just get 2. And let's simplify this expression a little bit. It's e to the I, Well, I've got a third multiplied by 0, so that's just giving me 0 plus 2k pi over 3. And every time I change my k, I'm going to get a different root. So let's start off with k equals 0. In this case, I've got 2e to the I, and k is 0. So this term becomes 0. If I have k equals 1, then I have 2e to the I, and my k is 1, so this is 2 pi on 3. When k equals 2, I get 2e to the, that's a 2 now, so it's I 4 pi on 3. And if I did go further and I put in k equals 3, you could see that this would be EI, I'll just write it over here so you can see it. If k were equal to 3, it's 2EI to the 2 pi, because I've got a 3 here and that cancels, but e to the I 2 pi is just the same as 2e to the I 0. And so k equals 3 would get me back to this place, and so on. So I would just continually cycle through these three numbers. So having more k's here isn't going to get me any more answers. Now this one where you'll see it's 4 pi on 3, and that's not normal in the normal range of argument that we would write that. So here we would write this as 2e to the minus I 2 pi on 3. Okay. All right, so I've just written our cube roots up here on the top of the page so we can see what they are, and now I'm going to try and draw them in the complex plane for you. So here's the real axis, here's the imaginary axis, and let's start off with Z1. So Z1 has angle 0 or argument 0, and it has modulus 2. So it's going to be on the positive real axis Z1, and that's the number 2. You'll notice that the second root, Z2, also has modulus 2, so it's going to have the same modulus as the first one, but the angle it makes with the real axis is 2 pi on 3. So it's going to be in the second quadrant, and it's going to have modulus 2. So that's my point Z2, and that angle is 2 pi on 3. And the last one is the complex number 2e to the minus 2 pi on 3. So again, it's got the same modulus, but now the angle is minus 2 pi on 3. So it's in the third quadrant, and that's Z3, and that angle is minus 2 pi on 3. Okay, so there's a couple of things that you should notice about this setup. First thing is that we were looking for the cube root, so we were looking for the complex numbers z whose cube was equal to 8. So here our n was equal to 3, and we got 3 solutions. The second thing that you will notice is that when we drew the complex numbers in the complex plane, all of the complex numbers have the same modulus. So if you think about drawing a circle of radius 2, all those complex numbers that we just found will sit on the circle of radius 2 because they all have the same length. The other thing to notice is that the angle from here to here is 2 pi on 3, the angle from here to here is 2 pi on 3, and the angle between here and here must also be 2 pi on 3 because that's what I've got left over. And so the distance between each of the complex numbers that I've drawn is the same. It's always 2 pi on 3. So those things aren't, none of the things that I've just mentioned are accidents of this example. That will always be true. So when you find the nth roots, they will divide 2 pi into 2 pi on n segments. And there will be n of them. They will all have the same modulus. So they'll sit on a circle with radius the modulus that you found. So the last thing we need to do now is write our complex roots in Cartesian form. So that just means we take the complex exponential form and expand it out. So I've got 2 e to the I 0 is just cos 0 plus I sine 0. So cos of 0 is just 1 and sine of 0 is 0. So this is just the number 2, and that's the complex root that we would expect if we were solving it over the reals. The next root is 2 cos of 2 pi on 3 plus I sine of 2 pi on 3. So that's 2, and the cosine of 2 pi on 3 is going to be negative a half. The sine of 2 pi on 3 is positive root 3 on 2, and if you can't see that immediately, have a look on the triangle that I've drawn up in the corner. So this is just minus 1 plus root 3i, and the last one is 2 cos of minus 2 pi on 3 plus I sine of minus 2 pi on 3. And that's going to be in the third quadrant. So cos is still negative, so that's negative a half, and sine is negative there as well, so that's negative root 3 on 2. So this is minus 1 minus root 3i. So they're the three cube roots of 8 when you're solving over the complex numbers. So from here to the end of this short section, there are a couple more questions for you to try, and if you get stuck, we'll do them when we come into class on Thursday. The next video will deal with the last topic in this section on complex numbers, and that will be looking at roots of polynomials. So we'll do that in the next video. In the meantime, don't forget to try some of these examples. Okay, see you soon.